So, welcome to the classes of GPU architectures and programming. In the last lecture, we have been discussing about a bit on this usage of shared memory. I mean, how the shared memory is configured, and in general, how global memory transactions are really happening. If you remember the curve that we were showing, that based on the different ways I am doing access of an array, whether it's an offset based access or a strided access, we could see that the memory bandwidth that was exploited, that is the number of global memory transactions per second that were happening, I mean how it was really getting affected. So, after that we also pointed out that there is really a share, I mean how to actually configure shared memory and the L1 cache, what are the related CUDA commands for doing that. So, now we will see how I can exploit this shared memory that is present in each of the symmetric multiprocessors, streaming multiprocessors, and in each of the streaming multiprocessors, and how they can actually help in accelerating parallel algorithms by suitable programming techniques. So, just as a recap, let us consider our very common and popular matrix multiplication kernel. So, this is the usual code of matrix multiplication kernel, which you might recall from our earlier examples. So, all that we are doing is there is a if statement which is basically checking whether the I and j, that is the location of the row and column that we are trying to access in the matrix, whether they are inside their relevant bounds. By the way, the row and column positions we are figuring out again by using the block ID x and thread ID x, block ID y and thread ID y variable values. So, each thread for its unique combination of block IDs and thread IDs would be able to find out a unique I and j. Then it should check whether the I and j are inside the memory range of the matrix, and then each thread will get inside this for loop. So, as you can see, this is a for loop running from 0 to n minus 1. So, essentially we are talking about multiplying two n cross n dimensional matrices. So, the thread would essentially multiply the elements of one row of matrix 1 with the elements of the corresponding jth column of the matrix 2, and it will essentially sum it up, store it in p value, and this value would finally be transferred to the target matrix location, the output matrix location, this dp here, right. So, in terms of a figure, this is the per thread activity. So, the thread I have launched for accessing ith row and jth column. So, I would actually prefer this picture in the flipped way basically. So, if we look into the access pattern here, so all that we are doing is we are figuring out an I and the j. So, I is the row index and the j is the column index. So, just to match with it, just consider the figure in a flipped way. So, just think that this is matrix 1 and the next one is matrix 2. So, essentially the thread will navigate through the row, the ith row and the jth column, pairwise multiply the elements and add, and finally figure out the final output value for the ith row and the jth column of the output matrix, right. I mean, this is the usual way we do matrix multiplication. So, what is the total number of threads that are getting launched for computing the output? So, definitely the total number of threads have to be used to equal to the number of elements in the matrix, because each thread is responsible for computing one element in the output matrix, right. But observe something important here with respect to the memory accesses performed by the threads. So, the same row and column is accessed multiple times by different threads. Why would we say that? So, if we draw up the simple figure here, So, for computing element I comma j, I would need to access the ith row entirely and also the jth column entirely. So, if I consider some thread I j, so essentially what is it doing? It is essentially accessing row I, let me say row I 1 for matrix 1, and this is matrix 2, and this is matrix output, and column j of matrix 2. Now, let us look at the entity I j plus 1. So, for that I would have another thread, so what is the row and the column that this thread would be accessing? So, I comma j plus 1 has to sit in the same ith row side by side with I j, right. So, this the thread which is responsible for computing the ith row j plus 1th column element of the output matrix, if I call it T I j plus 1. So, essentially what is it going to access? It is again going to access the ith row of the first matrix and the j plus 1th column of the second matrix, right. Now, let us consider some other entity. Let us consider the point I plus 1 j. So, what is the different memory, what are the different memory locations that the thread which will compute for this element will be accessing? So, let us call this thread T I plus 1 comma j. So, essentially as we can see, so the first one accessed ith and jth, the second one had accessed ith and j plus 1th column, right. And for this so I am essentially doing an access of the I plus 1th row and the jth column, right. Okay. So, let us again take another example just for completeness. So, I have then considered 4 nearby locations here. So, I plus 1th row and j plus 1th column, right. So, then I would be having the this new thread which has been launched for I plus 1th row and j plus 1th column, that would be accessing for first matrix I plus 1th row and for the second matrix the j plus 1th column, right. Now, see what is really happening. So, what is the total for computing these 4 elements, what is the total number of rows and columns that we have accessed? Okay, we have accessed 4 total number of rows and columns, that is to be specific 2 rows and 2 columns, but as you can see there is lot of common access. So, for an example, the ith row has been accessed separately by 2 threads who have been computing for this position as well as this position. So, the ith row has been accessed by both these threads. Similarly, the I plus 1th row has been accessed by this thread and this thread, right. So, I would say that is a performance loss. Why? Because one thread has already accessed the data from the global memory. Now, again I am asking another thread to access the same data the same locations from the global memory. Why? For doing the computation of a different position. Now, of course, one may argue that some of this will be saved in the cache. Well, we are talking about GPUs where the caches are really small, right? So, considering that we are looking into performance of our programming for very large matrices, the savings won't be great, which would mean I am kind of having these duplicated accesses from the global memory. This will be a huge performance issue. Why? Because every global memory access is extremely costly, order of magnitudes costly. So, the warps which will essentially access this global memory would stall for a lot of time, right. So, if I am trying to do the matrix multiplication in a nice way, this will definitely not be the good algorithm for doing that. So, again just to give an example again. So, essentially as we can see, the ith row would be accessed by, I mean if we are trying to speak in terms of some hard numbers. So, the ith row is getting accessed how many times overall in the computation. Of course, for in total in the output matrix there would be n elements in the ith row. Using this naive algorithm, I am bringing elements from the ith row into the memory so many times, right, n number of times by separately by each of the threads. So, that does not make sense. It would have been much better if data brought in from the global memory would have been useful for the computation by some other thread. As you can see that each thread is bringing its own row and own column from the global memory, but if it was the case that whatever thread I brings, thread Tij brings can also be used by the thread Tij plus 1, now that would have been much nicer, right, because both of them bringing the data of the same location multiple times does not really make sense. So, but the question is, okay, they may not be doing the computation at the same time, the thread Tij and Ti plus 1j, Ti plus 1 or Tij plus 1, thread Tij and thread Tij plus 1 may not be active together at the same time. So, in that case although since they are not active together in the same time, where will the data be resident, right. So, that also is an important thing. So, essentially for this purpose we can exploit the shared memory that is located in the same in the streaming multiprocessor. As we know that the shared memory is offering a consistent view to all the threads inside a block. Hence, threads operating inside a block can actually collaborate among each other. Threads operating into, or threads let me put it the other way around, the threads operating inside a block can bring in data in such a coordinated manner that the data required by one of the threads in the block is also useful to some other thread inside the block if they are brought from the global memory and they are made resident in the shared memory location. Why? Then each of the threads inside the block would be accessing the data from the shared memory location, and that access will be much more faster. So, the point to be noted here is we should try to minimize the refetching of data multiple times through global memory loads by different threads for doing the similar activity on different data points but using the same locations from the global memory. The alternate option is make the threads working inside a block collaborate among each other by bringing the data from the global memory and putting the data in the shared memory. Why? Because as we have already discussed that the shared memory view is consistent for all the threads inside a block. So, they can actually use the data, that means for doing their own part of the matrix multiplication computation, and while doing that they, instead of doing global memory loads, they will be actually loading data from shared memory, which is much faster because the shared memory is on chip and it is located inside the SM, much near to the scalar processors or the SP cores. So, what would be, I mean again just consider this picture flipped here. So, what would be the number of memory accesses required overall? If I am doing a naive matrix multiplication computation? Well, I mean, if I don't consider the global memory coalesced accesses, then essentially what is going on? For doing computation for each location in the output matrix, I need access to one column and one row of data, right? So I need access to n elements from a row, and I need access to n elements from a column. So that's n plus n, that's 2n. So I would definitely, the thread which is doing this computation would require access to 2n number of elements from the global memory. So n elements from a row, so this is the total number of memory elements that one thread would access, and overall how many threads do I have? So overall I have n square number of threads. So this is the total. However, the number of elements accessed is not equal to the total number of global memory transactions that would be going on, right? Just recall our knowledge of memory access coalescing. So whenever I am doing access for a column, so whenever I am doing access of this column, the number of global memory accesses, I mean, I am considering that n is very large. So since n is very large, the access of any column location and the access of the previous or the next column location is never going to be coalesced. That means they will never be brought from the global memory by a single global memory transaction. Why so? Let us recall, what is the width of a global memory transaction? So as we have discussed earlier, so as long as, so if since currently the warp width we are considering for modern GPUs is 32, so the global memory transaction would essentially bring in 128 consecutive bytes in one byte aligned access. Again, I would just repeat the part byte aligned access like we discussed earlier. So as long as this n is going to be larger than 128 bytes, these accesses of these consecutive locations in the column will all be separate global memory transactions, right? So for computing for one location here, for n of the column elements, I would end up with n global memory transactions. However, that will not be the case for the row. Why? Because in the row, all these elements in the final DRAM, they are all sitting side by side, right? Because we all know that we are following a row measure kind of setting in the RAM. So all of these elements are going to sit side by side. They are consecutive elements separated by 4 bytes considering an integer matrix, right? So out of this n, the consecutive 32 would be brought by a single transaction, right? So, assuming that these accesses are all byte aligned, that means n is divisible by 32 here, the number of accesses we would have is n by 32, right. Now, of course, I mean if n is not divisible, essentially it would be an n by 32, you take the floor and plus do one access more, something like that. I mean we can always assume here for our simple purpose this is divisible. So, I have got these many accesses for one element. So, the total number of accesses is n square times this. Now, of course, this is the actual figure, that is the total number of global memory transactions would be this. Considering 32 as very small, if I am considering a very large matrix, significantly large matrix, I can approximate it as n cube, but of course, that will hold for a very large, n is very large. Okay. Now, we would like to exploit two things here. First of all, the fact that consecutive accesses in the row are going to be coalesced, and the other fact that we were discussing earlier, that I can make use of the shared memory, threads inside a block can collaborate among each other, and in that case many of the global memory loads would be replaced by the shared memory load, and that would provide a lot of acceleration in terms of the execution of the code, right. So, if I do this optimization, then what we get is for an algorithm for doing matrix multiplication using tiling. So, in summary, we would say that the strategy we are going to use is to use a shared memory which will reduce the global memory traffic. So, what we will do is we will partition the matrix data space into subsets which are known as tiles in such a way that each tile fits into the shared memory. So, consider that I can fit each tile into the shared memory, right. I mean that is how we will design the tile size, right. So, as we have been discussing earlier, the threads inside the block will then collaboratively load tiles into the shared memory before they use the elements for doing the dot product calculation here. So, that would lead to kind of much more complex algorithm for deciding on that. We'll talk about that algorithm in the next lecture. For the time being, let's get comfortable with the idea that the shared memory can be used collaboratively between the blocks, between the threads inside a block, and when I am also going to use the other important parameter here, which is that whenever I am doing global memory loads, I am always able to do a coalesced access of the elements in the row. With this, we will end this current lecture. In the next lecture, we will go deeper into the algorithm. Thank you.